And hi, YouTube back to our YouTube back to our turbulence modeling discussion. So today we want to talk about the Prandtl number again, turbulent Prandtl number, and its variation. Because of course, in the way we derived it, it was kind of for a special case of a boundary layer flow in the law region. Okay, remember we were deriving this, and we said that this quantity we can sort of do away with that. And we said that this for Prandtl number, I mean more or less equals to 1. This thing here that I'm highlighting, it should be constant. But of course we know that when Prandtl number deviates very far from 1, the magnitude of these fluctuations will start to change, alright, relative to each other. Okay, so the ratio between this and this will start to change, and we might see that having some effect on this turbulent Prandtl number, because this, remember, it could be a function of Reynolds number and the Prandtl number. Okay, this is the molecular Prandtl number, or just the Prandtl number we are used to. So the Reynolds number will, play a role in this friction velocity here. Of course, you have more heat flux over there. But the Prandtl number will affect the ratio between these fluctuations here. Okay, because if let's say you have a fluctuation that's caused by some turbulence, if you have a low Prandtl number fluid, the magnitude of the temperature fluctuations will be very small because it's conducted away very quickly. All right, at least the averaged fluctuations will be very small. And then, of course, we actually substituted these expressions from the law region. So this Prandtl number, 0.9 or 0.55, this is usually more applicable to the law region. And experiments also show that you can sort of get away with using this Prandtl number throughout the rest of the bulk fluid. Okay, so we want to really put these to the test. Okay. We want to put this to the test, by doing, or rather looking at some experimental data. So according to this paper, the papers I want to introduce to you, it says one of these things is here, the turbulent Prandtl number in the near wall region for low Prandtl number gas mixtures. Okay, and this one also is good because it says this one is about the turbulent Prandtl number. Where are we? This is a very good summary paper to kind of get you started into all these special cases. Alright, so experiments show that Prandtl number is roughly constant inside the free shear zone. Okay, so in the free shear zone, anyway, I'll just put this citation here to tell you where I got this data from. But anyway, Prandtl number is roughly constant in the free shear zone, similar in value to the log-law boundary layer. Okay, but there's some actual variation below the log-law layer, okay, from this paper. And one of the simple models for that is as follows. Okay, so experiments were done using air and water, which have a Prandtl number approximately 0.7. Now remember I said that water has a Prandtl number at room temperature and pressure of about 5 or 7, somewhere around there, depending on the temperature you go. Well, how do you get the Prandtl number of 0.7? Actually, what happens is that if you pressurize water and you raise the temperature up beyond the normal atmospheric boiling point of 100 degrees C, so you can raise water to about 180 degrees, 200 degrees, even higher, you will get Prandtl number around this range. So this is how you will get water to have this sort of Prandtl number. Okay, so it has to be pressurized. Anyhow, so the turbulent Prandtl number as a function of some distance from the wall, it will be 0.855, and then this 1 minus hyperbolic tangent of whatever factor this is inside here, 0.2 y plus minus 7.5. So what you would actually see in the graph, so-called, will be something like below y plus equals to 30. Okay, below y plus equals to 30, let's say you have Okay, you have this Prandtl number, turbulent Prandtl number, and you have y plus here. So at like 30 and below, it will sort of shoot up to I guess a value like of 2. This is as close to the wall as they could get. Well, I wouldn't say that close. Okay, so somewhere here you have a Prandtl number of 2, and I mean somewhere down the road you have a Prandtl number of 1, and it sort of flattens out here. So as you have a 0.855. Okay, so this is what the graph actually looks like. And as you increase y plus all the way up to even 1000, y plus equals to 1000, right? So let me just make a note. It goes up to y plus equals to 1000. Alright, this y plus equals to 1000, and you have a very steady, Prandtl number. So this kind of shows that in the log law region, where y plus more than 30 up to y plus equals 1000, you can see that the Prandtl number is more or less the same. This was from experimental data. The place where it starts to vary is in this buffer zone, where the profile will start to differ, and then you'll start having this rapid increase, so to speak. Okay, but that's something you just kind of need to take note of, as in very much closer to the near wall region. But of course, as with everything, if you manage to run your CFD code and you still get satisfactory heat transfer results or natural convection results, I mean, even with a Prandtl number of 0.855 or 0.9, it can, if it works, it works. All right, so it's not a strict you have to follow rule, but if you can generate a simulation that matches experimental data, that is the bottom line. Okay, but this is just for your knowledge and just to show that Prandtl number can vary with y plus, because as you go closer to the wall, of course your Reynolds number starts to change. Remember, your Reynolds number starts to change, and of course your temperature and velocity profiles also start to change. So that's something you need to take care of. Alright, the other interesting case where we don't talk about fluids near Prandtl number equals to 1, there are two important cases. One is liquid metal, and then one is which is a low Prandtl number, and then the other is the oil and glycerin, which has a very high Prandtl number. How low? Prandtl number of liquid sodium is about 0.008. So this is the kind of order of magnitude you are expecting for a low Prandtl number fluid, where this kind of effects become more important. Whereas oil and glycerin, oil has a Prandtl number of, depending on what kind of oil, it can have Prandtl number of about 16 to 18, 40, 60. If you have very, I guess crude oil, it can be high. And glycerin has a Prandtl number in the thousands. Okay, glycerin has a Prandtl number in the thousands, probably because it's a very poor thermal conductivity and very high viscosity. Okay, so that's where you get a very high Prandtl number fluid. So for liquid metal case, my Prandtl number is very, very low. I mean 0.08 or 0.008. There were correlations developed for it, and the average Prandtl number you get, average Prandtl number you get is about this one I think I should cite. This one is from an extended Kays and Crawford model. This is, this one is by this guy. So did I put it here? Okay. Oh yes, I did it over here. I put it in this part. Of course you'll find it in the description, but here's the Weigand and Ferguson, all this extended Kays and Crawford model for turbulent Prandtl number model. This is for liquid metals. So I'll scroll back down and I'll just describe the model to you. No derivations here, but just roughly get the idea. That's good enough. Okay, so firstly we have an average sort of average Prandtl number, turbulent Prandtl number, and it's over here. It's dependent somewhat on this Reynolds number, and that's important to note because remember at the low-Prandtl number, I think this term here becomes a little bit more important, and this in general is a function of the Reynolds number and the Prandtl number. So I guess one of the ways you can actually extract that out, you can actually just, you have this 0.85, you bring it out, and then you divide the inside by 0.85, and then you divide this by 0.85. Okay, so this thing becomes the F of the Reynolds number and Prandtl number. Okay, this is an empirical model, but this is one of the ways you could find it. All right, so yeah, I guess you could separate it out, but again, this is not fully accurate, of course, because for liquid metals, the log region actually has funny shapes. When I mean funny, I mean that they do not share the same shapes as for Prandtl number equal 1. So this is doing this is like, okay, it's not really the direct comparison. Okay, so if we want to make this comparison, this one doesn't quite hold so well. Okay, so anyway, it doesn't quite hold, but it's interesting to see. Yeah, it doesn't quite hold exactly, but it's interesting to see the Reynolds number and Prandtl number dependence. Okay, so that's just for information. Okay, so this one is okay, use with caution. Okay, so not an official correlation. All right, so it's just to help you understand what's some of the processes going on, but this is not the actual thing, but it's just interesting to see the Reynolds number and Prandtl number dependence. Okay, so like any fluid, the Prandtl number, turbulent Prandtl number will sort of deviate away from the wall, and this was the Kays and Crawford model, where you have okay, Prandtl number as a function of the following. Okay, first you have this free shear thingy, free shear Prandtl number, which we kind of take inspiration, or rather Weigand, I don't know how to pronounce his name. He takes inspiration from this model here, and this model is done by I don't know how to pronounce, and okay, Reiki? I don't know, sorry, probably not pronounced the name right, but this is what they came up with. So to develop something that's nearer to the wall, this Kays and Crawford, they took inspiration from there to develop, there's a free shear Prandtl number, or in the paper you see the Prandtl number, turbulent Prandtl number at infinity, which means it's in the bulk fluid or the free shear zone. So this will appear here, or it will appear here, and it will appear here. When you see C here, it usually refers to a number a constant calibrated at 0.3, and you also see this thing called something that looks like the Peclet number. Okay, so here we see PET as if it's some turbulent Peclet number, and that is equals to the Prandtl number times nu t divided by nu. So this is how this turbulent Peclet number comes about. And of course the wall distance dependence is implicit because nu t is actually dependent on y plus. Yeah, so nu t actually kind of varies. Okay, nu t is some function of y plus. So to get the turbulent Prandtl number, we need to know the nu t profile near the wall. So we can say that the turbulent Prandtl number is a function of nu t, kind of implicitly like this. So this is where the Prandtl, the y plus dependence comes about. But I'm not going to go too much in detail over here because there are lots of models again. So anyway, just for reference, your normal Prandtl number or Peclet number is equals to Reynolds number times the Prandtl number. So this is just what, for reference, your normal Peclet number is supposed to be. So Prandtl number is common among both of them, except here they use some ratio of the viscosities here to give some dimensionless number. Okay, some dimensionless number. So that's what they use over there instead of the Reynolds number. Okay, so we have this kind of case. Okay, so this is the Peclet number. Then we have a Prandtl number much bigger than 1. So there will be some correlations for that. Okay, so these are flows in the tube or pipe flow. Now, of course, getting measurements near the wall are difficult for high Prandtl number fluids because it's a little bit hard to measure it near the wall, but there are some correlations available for certain Prandtl numbers. But I'll just present what are some of these correlations. First, these are for bulk Prandtl numbers in pipe flow. It's not boundary layer. This is like the average Prandtl number. One representative Prandtl number for the whole fluid, so to speak. And they try to match it to some data, or like sort of back calculate it. So you have turbulent Prandtl number like this. It's a function of the Prandtl number, right? From 1 to 45. They use data for water from 5 to 180 degrees C. Remember, this is pressurized water. CO2 at 25 degrees C, or and ethylene glycol at 70 to 100 degrees C. So Prandtl number, the turbulent Prandtl number is 1.01 minus 0.09 Prandtl number to the power of the 0.36. This is just empirical data fitting. Likewise, over here from 145 to 1800, a Prandtl number using ethylene glycol at 0 to 24 degrees C, glycerin at 50 degrees C. Prandtl number equals 1.01 minus 0.25 times a natural log of Prandtl number, if I'm not wrong. So if you want to go and check where I am getting the numbers from, it is from this it's from Kirillov's paper. Kirillov's paper, he has a, I think it's a he, but yeah, here's the table of Prandtl number versus turbulent Prandtl number. Okay, so this is from Kirillov. His paper is here. Okay, let's go up. And yeah, this is where we are. Kirillov. Yeah, this guy, Kirillov, heat exchange in turbulent flow part 1, turbulent Prandtl number. So do go and check his paper out. You should be able to find some of the Prandtl number correlations there. For high Prandtl number especially, there's a table towards the end of his paper. Anyway, so we come back to this, and I'll just go through the rest of it. Prandtl number equals to 1.01, or turbulent Prandtl number equals 1.01 minus 0.25 natural log of Prandtl number. And for high Prandtl number, 1/800 to 112,000 ish, Prandtl number is equals to 0.99 minus 0.44 times hold on, yeah, made a typo here. This should be 0.5, not 0.05. Okay, so these are the correlations we have here. Yeah, just want to double check. 1.01. Yeah. So this is what the correlations look like for these various Prandtl number ranges. You can go and search online for his paper, or you can just take my word at face value. So of course there will be some correlations for near wall Prandtl number variation, but for high Prandtl number fluids there may be some difficulty in that, but otherwise that's what you have. Okay, there are near wall correlations for some Prandtl number ranges. Yeah, but that's probably for next time if I have the time. Okay, so thanks for watching. I'll see you guys again. Please leave a like and subscribe if you do find this content useful. See ya.